Probability is a measure of the likelihood of the occurrence of some event. And we measure that probability and assign a number to it just by using a rather simple fraction. It's the fraction of favorable outcomes over possible outcomes involved in some kind of situation. Let's talk about a little vocabulary here. An experiment is like rolling a six-sided die. Now, the outcome of this is kind of a happening, and we don't know what the outcome is going to be. So we have an experiment on our hands. Now, the outcomes. Well, what can happen when we roll a six-sided die? Well, we can roll a 1, or we can roll a 2, or a 3, or a 4, or a 5, or a 6. So those are all of the outcomes. Now, when we list all the possible outcomes, we have a set of items called the sample space. And that's kind of important, because if this is this set of all possible outcomes, then that's what goes into our denominator of this fraction for probability. It's the number of possible outcomes that we want here. And so in problems involving rolling a six-sided die, the 6 would go in that denominator. Okay, an event is something like, it's always a subset of the sample space. It's kind of like rolling an even number when we talk about this kind of situation. Now, even numbers, we could assign a set to it. We could write the items that are possible for even numbers. It'd be 2, 4, and 6. So then we can get into the idea of writing a probability. It's the probability of some event. Now, the probability of an even number means, let's see, what are the favorable outcomes? Well, we listed those in set form over here. There were 3 of them. And the possible outcomes, well, there are 6 possible outcomes. That's the number of items in the sample space. So 3 over 6, or 1/2, or 0.5. Now, just by the nature of the fraction involved in calculating probabilities, we can probably recognize that the probability number is normally going to be a number between 0 and 1, because the favorable outcomes is generally a subset of the possible outcomes. Now, if a situation is assured, it will happen, then the favorable outcomes will be the same as the possible outcomes, and we'll have a probability of 1. Now, if there aren't very many favorable outcomes, and the possible outcomes are perhaps a large number, then we have a small number over a large number, and therefore the probability of occurrence is very small. So as the probability number approaches 0, then the likelihood of the occurrence of the event grows less and less. And as the probability number approaches 1, then the likelihood is greater and greater. Okay, so that's the general idea. Suppose we're talking about rolling a die now, and we want the probability of rolling a 5. Well, let's see. Favorable outcomes over possible outcomes. How many 5s are there? Well, there's only 1, and the possible outcomes would be 6. Now, what about the probability of rolling a number which is not a 5? So that would be the probability of a 1, a 2, a 3, a 4, and a 6. Well, there would be 5 of those out of the possible outcomes 6. Now, notice that these two together give us a probability of 1. If we were adding these two probabilities, we would have a probability of 1. And that kind of makes sense, because the only possibilities when we're talking about rolling a 5 or rolling something that's not a 5, those two together would be an assurity, you see. And so this idea that 5, not 5, these are called complements of one another. And we'll talk more about the complement idea in just a little bit, because it becomes a strategy for figuring a probability. Okay, now just to make sure we understand, it kind of goes along with the idea of complement, but if the probability of some event is equal to 0, you see, then it can't happen. And as we approach 0, it becomes less likely. But if we arrive at 0, it can't possibly happen. And in a similar way, if the probability of some event is 1, then it must happen. And as we approach 1, it is more and more likely to happen. All right, let's talk about 2 items in some kind of experiment. We have tossing a coin and rolling a die. Now, let's calculate the probability of tail and 4. Tail and 4. Now, first of all, we might think of, gee, how many favorable outcomes are there? Well, let's see, how many ways can we toss a tail and roll a 4. Well, there's only one way to do that. Now, sometimes it's valuable in situations like this to actually list the entire sample space. If the sample space is relatively small, then that's a really safe way to approach the problem. For example, here we might say, well, the sample space, all the possible outcomes now would be, let's see, head 1, head 2. We talked about this in the last section, I believe. Head 3, head 4. And the head can be associated with all of the numbers up to 6. And in a similar way, tail can be associated with all of the numbers up to 6. So we have a T3, a T4, a T5, and a T6. Now what we're talking about in this problem for the probability of tail in 4 is the probability of this item, that one single item. So there's only one way to do that. Out of the possible outcomes, well, that's all the items in the sample space. There are 12 of them, so the probability is 1/12. Now the probability of head and odd. Head and odd. Well, now it's really handy to look at the sample space because we can easily identify head and odd. Head with 1, that's an odd number. You see the 1 is an odd number. Head with 3, head with 5. And that's the only those are the only items in the sample space that's head and odd. 1, 2, 3 out of 12. 3 over 12 we reduce to 1/4. A lot of times, by the way, probability numbers are written as decimals, and it's okay to write them either way, and the interpretation is exactly the same. If the decimal number is near 1, it's more likely to occur. Near 0, less likely to occur. Suppose we have a deck of cards, and we talk about some probabilities of drawing a card or a group of cards, maybe, sometimes at random. What about the probability of drawing the king of hearts? Now, we understand the arrangement of a deck of cards. And that arrangement is that there are 52 cards in the deck and there are 4 suits. Let's see, spades, hearts, diamonds, clubs. And in each suit we have ace, king, queen, jack, 10, 9, 8, and so on down to 2. So there are 13 cards in every suit. And there are 4 suits. 2 of them are red, 2 of them are black. Now, by the way, I might mention that just a comment here about using dice and coins and cards in this study of probability. It's not that I'm trying to promote the idea of gambling. Quite the contrary is the truth. If you know something about probability, then you know to stay away from those kinds of gambling activities. But those activities, the deck of cards, the dice and so forth, give us a nice way of studying probability because the situations are random, that is drawing a card out of a deck of 52 different ones, and there are different combinations that are possible within the deck. Those are aspects of probability that need to be studied. Okay, let's go with our probability calculations. The probability of the king of hearts. How many king of hearts are there? Well, there's only one card that is the king of hearts, and there are 52 cards in the deck. So the probability of drawing the king of hearts is 1 in 52. Probability of a red card. Well, in the deck, how many are red? Well, all of the hearts and all of the diamonds are red. There are 13 hearts and 13 diamonds. Gee, that's 26 cards that are red out of the deck of 52 cards. This can be reduced to 1/2. So the probability is 1/2 or 0.5 of drawing a red card. What about the probability of drawing a diamond? Well, how many diamonds are there? You see, you're always thinking favorable outcomes, possible outcomes in every case here. So how many diamonds? 13 out of the deck of 52 cards. Now this reduces to 1/4. 1/4 of the deck, you see, is diamonds. The probability of a 7. Now, sevens, how many 7s are there? Well, there's a 7 in every suit. So there would be 4 7s in the entire deck and 52 cards, so the probability of drawing a 7 would be 4 in 52, or 1 over 13. Now, the probability of not 10. Probability of not 10. That would mean, let's see, the favorable outcomes would be all of the cards that are not 10s in the whole deck. We'd have to count all the aces and all the kings and all the queens. We'd have to count all of those cards, you see, and then put that over 52. It's a little easier, though, in calculating the probability of not 10. This complement idea comes into play here. It's a little easier to count the cards that are 10s and then make a calculation for the probability of not 10. Now, let me show you what I'm talking about here. Just conceptually, the notion of 10s and not 10s is the notion of complements adding to 1. That is, the probability of some event plus the probability of not that event occurring is equal to 1. You see, these two probabilities together is equal to 1. It's assured that either this will happen or that. You see, now let's use a little algebra on this. The probability then of not E is equal to 1 minus the probability of E. Now, all I'm doing here is I'm subtracting this on both sides, so I get this. So another way to approach the notion of the probability of not 10 is to calculate 1 minus the probability of 10. So this is equal to 1 minus the probability of 10, and we know the probability of 10 is the same as the probability of 7 here. We think through it in the same way. So this is 1 minus 1/13. 13/13 minus 1/13 is 12/13 for that probability. What about the probability of drawing a full house in a deck of cards? Now, a full house is a poker hand consisting of 2 of a kind and then 3 of a kind for the 5 cards in the poker hand. All right, now that probability, this probability is going to involve the aspects of permutations and combinations that we talked about before. Here's how we think through the problem. We begin with the idea that this probability is found by finding the number of full house hands, all of the full house hands that are possible up here. And then down here, all the possible poker hands. You see, the probability is favorable outcomes over possible outcomes. Favorable outcomes is full house hands. Possible outcomes, all possible poker hands. Now, what about full house hands? That really is the tough part of the problem, I think. Now, full house hands are composed of pairs and 3 of a kind. Now, how many pairs are possible? Well, let's see. Let's go over here and think about that. Now, here's the structure of a deck of cards. We have spades, hearts, diamonds, clubs. In each one, we have ace, king, queen, jack, 10, all the way down to 2. All right, now consider just the kings. If we consider just the kings, then how many pairs are possible with just the kings? You see, now, we could have these 2, we could have those 2, we could have those 2, we could have these 2, we could have you see? So it's the combination. Now, we're talking pairs here. We're talking a group of 2. So it's a combination idea. It's a combination of 4 things, but we want only 2 of them. The combination of 4 things taken 2 at a time. So really, we're calculating the combination of 4 things taken 2 at a time. Now, this is, let's see, the calculation is made as, in the numerator, we have 2 factors starting with 4. So we have 4 times 3, and in the denominator, 2. 2 and the 4 cancel, 2 times 3, 6. So there are 6 pairs of kings possible in the group of kings. Now, how many possible pairs are there altogether? If there are 6 right here, but there are 13 different items here. There are 13 items in every suit, you see. And so we have 6 times 13 for the number of pairs. 6 times 13. Wow, so that's the number of pairs. Now, what about 3 of a kind? Well, let's examine that in the same way. What about with the jacks? If we're thinking about 3 of a kind, we think about all the different ways that we can have 3 jacks out of these 4 jacks. Well, that again is the notion of combination. And it is the combination of 4 things taken 3 at a time. And we know that a nice technique for making this calculation is the combination of 4 things taken 1 at a time. That's the fast way if we're using this number of factors in the numerator and all that kind of stuff. So this is 1 factor in the numerator starting with 4, and in the denominator it's 1 factorial, and so this is simply 4. All right, so the number of 3 of a kind jacks is 4. So there are 4 of those. Now, What about, and we can have that situation in all of the different suits. But wait a second. We've already said that we've got a pair of something, and we can't have a situation where we have a pair of kings and also three of a kind with kings. So although we're going to count this three of a kind situation, if the pairs have already been selected, you see, then we can't count the items in one of the suits. So it'll end up being 4 times 12. Now, you might be saying, well, gee, what if the three of a kind was chosen first? Well, it's the idea that we have this 13 factor here and a 12 factor here. And I probably ought to use the same designation for multiplication in both places. But if we had chosen to calculate the number of three of a kind possibilities throughout the deck, then it would be 4 times 13. But then we would kick over here and say, then this would be 6 times the 12, you see. So the 13 and the 12 go in one of the other positions. At any rate, we multiply these various factors, and we find that the number of full house hands turns out to be 3,744. Okay, so that's going to go in the numerator of this fraction. In the denominator we have, well, let me write it down like this. So this probability of drawing a full house is, let's see, the number of full house hands, that's 3,744, over all possible poker hands. Well, that would be the combination of 52 items taken 5 at a time. You see, how many groups of 5 are there in 52? And that number is incredibly large. It turns out to be in the millions. It turns out to be 2,598,000. I have it written off camera, so I'm looking over and reading it. 598,960, I think it says. Now, does this probability mean very much to you with these large numbers involved like this? Go like this. Nope, doesn't mean very much. It's a pretty small number, but we don't know quite how small it is. A lot of times we like to see probability numbers written as 1 in so many. You know, that we have a feeling for that. If it's 1 in 20 or 1 in 5 or 1 in 5,000, we kind of have a feeling for that, for the likelihood of the occurrence of that event. Well, we can turn this fraction into such a thing. We can kind of force it into that situation. If we just take the numerator and divide by 3,744 and take the denominator and also divide by 3,744. Now, it may not go evenly. The 3,744 may or may not go evenly into the denominator. But even if it doesn't, we could use an approximation there and get a better feeling for the probability number. Now, if we did that here, divide both numerator and denominator by 3,744, we would get 1 as expected in the numerator, and in the denominator we would get 694. So the probability of drawing a full house hand is approximately 1 in 694. Sometimes the word "and" is used in a probability. That is, the probability of this and that. Sometimes the word "or" is used in a probability request. The probability of this or that. Well, when those two words are used, we can make the calculations a lot of times in a rather special way. Consider this problem. We have a deck of cards, and we want to calculate the probability of drawing a 5 or a jack. Now, the one way to make the calculation is like this. We can just add the separate probabilities of the 5 and the jack. That is, we can say, let's find the probability of drawing a 5 and add the probability of drawing a jack. Now, the probability of drawing a 5, since there are 4 5s in the deck, would be 4 in 52. Same idea with the jack. There are 4 jacks, so the probability of drawing a jack would be 4 in 52. Adding, we get 8 in 52, 8 over 52. We could reduce a bit, but let's not worry about that. The concept here is that when the two events here have nothing in common, that is, they're said to be mutually exclusive, when they have nothing in common, they both can't happen at the same time, then we can simply add the probabilities, the separate probabilities. Now here's what we do when they're not mutually exclusive. We have the word or involved, so that kind of tells us that we're going to add probabilities. But here we do have a card which is both a queen and a diamond, you see. So the probability of queen, the probability of diamond, they're not mutually exclusive. So what we have to do is perform a little subtraction here. Here's what we do. We find the probability of queen, we add the probability of diamond, and we subtract the probability that both of them happen. You see, so it's the probability of a queen, the probability of diamond, minus the probability of the queen of diamonds. So the probability of queen, well, there are 4 queens in the deck of 52. The probability of diamond, there are 13 diamonds, so the probability of drawing a diamond would be 13 in 52. And the probability of drawing the queen of diamonds, since there's only 1 queen of diamonds in the deck, it would be 1 in 52. Now the reason why we have to subtract out this 1 over 52 is because we're actually counting the queen of diamonds twice over here. So we have to subtract out one of them. And we're counting the queen of diamonds twice because when we find the probability of a queen, we say there are 4 queens in the deck. Well, one of these 4 queens is the queen of diamonds. So we're counting one of those queen of diamonds here. But here we have the probability of diamonds. There are 13 diamonds, but one of those diamonds is the queen of diamonds. So we're counting that queen of diamonds twice. So no wonder we have to sort of subtract it out here to get our calculation to come out correct. Okay. Now, we can extend the idea of using the word or, adding probabilities when we use the word or, by just saying that in all cases, let's just add separate probabilities and subtract the probability that they both happen at the same time. Then we don't have to worry about whether or not the events are mutually exclusive. In fact, we could have applied that idea up here. We could say, okay, we have the probability of 5 or jack, add the separate probabilities and subtract the probability that they both happen at the same time. The probability of drawing a card which is a 5 jack. Doesn't make any sense, does it? Well, of course it doesn't. So the probability of doing that is 0 out of 52. So that's the idea. Now, we have another special case when the word and is used. Suppose we're tossing a coin and rolling a die, and we want the probability that we toss a head and roll a 4. Now, we looked at this situation before. We said that, gee, if we're performing these 2 tasks, these 2 experiments back to back, then with our sample space, all the possible outcomes here would be head with 1, 2, 3, 4, 5, 6, and tail with 1, 2, 3, 4, 5, 6. So there are 12 items in the sample space, and there's only one item that's the head and then the 4. So it's 1 out of 12. Okay, so we make the calculation that way. Well, sometimes situations are complicated, and it would be worthwhile to kind of separate the calculation if we can. And we can separate the calculation a lot of times when the word and is used. And the separation is to figure the separate probabilities and just multiply them. Here's what I'm talking about. Here we calculate the probability of head, and then we multiply times, because of and, the probability of 4. The probability of a head in tossing a coin is 1 in 2. The probability of rolling a 4 and rolling a 6-sided die is 1 in 6. Multiplying those 2, we get 1 in 12, as we might expect. Okay, so that's the idea. Now, we can always do this multiplication of probabilities in situations involving and, as long as the 2 events are said to be independent. Now, all that means is that the outcome of one event doesn't affect the outcome of the other. That is, the probability, regardless of what coin we toss over here, it's not going to affect which die or which surface of the die comes up when we roll the die over here. So the probability of one doesn't affect the outcome of the other. Okay. Probability of tail and a number greater than 2. Well, let's separate them and multiply. The probability of tail, well, that's just 1 in 2. The probability of a number greater than 2. Number greater than 2, that would be 3, 4, 5, 6. There are 4 of those, so it's 4 out of 6. And now multiplying, we find that the probability of tail and number greater than 2 would be 1/3. A salesperson makes a sale at approximately 1/3 of the offices she calls on. If, on a given day, she goes to 4 offices, what is the probability that she will make a sale at A, all 4 offices, B, none of the offices, and C, at least 1 office? The probability of having a sale at all 4 offices can be thought of as the probability of a sale and a sale and a sale and a sale. And using the words "and" here gives us a tip-off that we can multiply probabilities. Now, so we're talking about the probability of a sale here, which is 1/3. And means multiply. A probability of the sale at the second visit is 1/3, and then sale at the third visit and a sale at the fourth visit. So 1/3 to the 4th power, or 1/81, would be the probability of sales at all 4 of those offices. Now, the probability of no sales. It's a very similar idea to this situation. If the probability of making a sale is 1/3, then the probability of not making a sale would be 2/3. So it would be the idea that we have no sale at the first office, and no sale at the second office, and no sale at the third office, and no sale at the fourth office. So it would be 2/3 times 2/3 times 2/3 times 2/3, or 16/81 as that probability. Now, here's the interesting one, in my opinion. The probability of at least one sale, at least one, that's saying the probability of making one or more sales. Now, one way to make that calculation is to calculate the probability of exactly one sale and add the probability of exactly 2, and add the probability of exactly 3, and add the probability of exactly 4. You see, that's a way to do this. But there's a better way to do it. Another way is to approach it using the complement of this business. Now, the complement of this means it is not the case that at least one sale occurs. You see, if at least one sale does not occur, then that means no sales. So it's 1 minus the complement of this, which is 1 minus the probability of no sales. Now, we just calculated the probability of no sales to be 16/81, so it's 1 minus 16/81, or 65/81. Pretty good probability then of having at least one sale in those 4 visits. Now, by the way, this complement idea, there is a notation associated with it here. And I want to show you that notation because you might bump into a problem regarding this. But if we're talking about the probability of some event A, then the probability of not A is the probability of A prime. That a lot of times is the notation for not A. Rather than writing the word not, we just put the little prime up here, and it means the complement of A.